Friends, welcome to the tutorial series on network analysis made simple. You know that time varying functions can be expressed in different ways. For example, they can be expressed by using statements or by mathematical model or by piecewise definition. During this tutorial titled Laplace Transforms of Piecewise Defined Functions, we observe the given piecewise definition, plot the function, represent the function using basic step and ramp functions, and find their Laplace transforms. Hope you will enjoy the travel. Friends, first let me explain the ways in which the given function can be expressed. Then let us represent the given function using piecewise definition. Consider a simple step function which occurs at t is equal to 0 as shown in figure. Expressing by statements, we can say that this function is 0 for t less than 0 and is equal to 1 for t greater than 0. Its mathematical model also you know. In fact, the mathematical model of this function is nothing but a piecewise definition. Therefore, a piecewise defined function is considered to be made up of a finite number of pieces. For example, in this unit step function, there are two events, one time t less than 0 and 2 for time t greater than or equal to 0. Consider another function shown in figure. By statement, this function can be stated as the function f of t is equal to 0 for t less than 1 second and 2, it is a ramp of slope or strength 4 divided by 2, that is 2 units between time t is equal to 1 second and t is equal to 3 seconds. And third, it is equal to 4 units after t is equal to or greater than 3 seconds. Friends, the above three statements can be expressed as a piecewise definition as shown. Hope you have understood what we mean by the piecewise definition. Now, let me define the piecewise defined function technically. Friends, a function is called as a piecewise continuous on the interval if the interval can be broken into finite number of subintervals. The function is continuous on each open subinterval. For example, in a step function defined earlier, f of t is equal to 0 for t less than 0 can be considered as an open subinterval. Similarly, in another function, f of t is equal to 0 for t less than 1 second can be considered to be as an open subinterval. In both of these subintervals, the function is continuous, meaning it does not have either discontinuities or jumps. Note that the function has finite limits at each end points of the subintervals. For example, f of t is equal to 1 for t greater than 0 is finite. Similarly, this function has three subintervals, one of time t from minus infinity to 1. This subinterval is open and the function is continuous in this subinterval. Another subinterval is between t is equal to 1 second to t is equal to 3 seconds. In this subinterval, the function is finite at both the ends. At t is equal to 1 second, f of t is equal to 0. At t is equal to 3 seconds, f of t is equal to 4. Similarly, at subinterval between t is equal to 3 seconds to infinity, at t is equal to 3 seconds, f of t is equal to 4, and till infinity, the function f of t is equal to 4, which means it does not have breaks. Hope you understand this. Friends, To emphasize the concept we have learnt, let us solve few numerical examples. Consider a piecewise defined function f of t. Observe the given function. Let f1 of t is equal to 0 for t less than 2 seconds. It means the function is 0 for t less than 2 seconds as shown in figure. Let f2 is equal to 4 into bracket t minus 2 for t between 2 to 6 seconds. During this interval of time t is equal to 2 seconds to t is equal to 6 seconds, the function is a straight line having slope equal to 16 divided by 4, that is 4 units, and has y-intercept equal to minus 2. Or we can say that the function is a ramp of slope equal to 4 units between time t is equal to 2 seconds to t is equal to 6 seconds. Observe that if we substitute t is equal to 2 seconds, we get f of t is equal to 4 into bracket 2 minus 2 equal to 0. Similarly, if we substitute t is equal to 6 seconds, we get f of t is equal to 4 into bracket 6 minus 2, that is equal to 16 units. Note that the function is finite between the interval t is equal to 2 seconds to t is equal to 6 seconds. Then let f3 is equal to 16, meaning the function is constant after t is equal to 6 seconds. All the three functions are shown in figure 1, and the resulting function, by limiting the end points, the function obtained is shown in figure 2. By representing the function using step and ramp functions, we get f of t is equal to 4 r of t minus 2 minus 4 r of t minus 6. By taking Laplace transforms, we get f of s is equal to 4 into e to the power of minus 2s by s square minus 4 into e to the power of minus 6s divided by s square. Friends, if you need clarifications regarding representing the function using step and ramp functions, I suggest you go through my earlier videos on special signal waveforms, on step functions and ramp functions. Friends, next let us consider another piecewise defined function f of t. Observe the given function. Let f1 of t is equal to t for t between 0 and 1 second, meaning it is a ramp of slope equal to 1 unit and it occurs at t is equal to 0 as shown in figure 1. Let f2 is equal to 2 for t between 1 to 3 seconds, meaning it is constant and is equal to 2 units as shown in figure 1. Finally, let f3 of t is equal to 0 for t greater than 3 seconds, meaning f3 of t is 0 from 3 seconds onwards as shown in figure. Friends, you see that all the three functions are shown in figure 1 and the resulting function is shown in figure 2. By representing the function using step and ramp functions, we get f of t is equal to r of t minus r of t minus 1 plus u of t minus 1 minus 2u of t minus 3. If you have doubts in obtaining this equation, I suggest you go through my earlier videos on Laplace transform of special signal waveforms. Friends, by taking the Laplace transforms of f of t, we get f of s is equal to 1 divided by s square minus e to the power of minus s by s square plus e to the power of minus s by s minus 2 e to the power of minus 3s by s. That is so simple. Friends, now let us take up one very interesting problem. Observe the given piecewise function. Let f1 of t is equal to 2 for t between 0 to 5 seconds, meaning the function is constant equal to 2 units, which is shown in figure 1. Next, f2 of t is equal to 0 for t between 5 to 10 seconds, meaning it is 0 between the two time limits which is shown in figure. Finally, let f3 of t is equal to e to the power of 4t after t is equal to 10 seconds. This function f3 of t is shown in figure 1. Considering the functions present between the specified subintervals, the function plotted is shown in figure 2. How we got that? Let me explain to you. The function f1 of t can be represented as f1 of t is equal to 2u of t as it occurs at t is equal to 0. This you know. At t is equal to 5 seconds, we have to add a negative step of 2 units so that f2 of t is equal to 2u of t minus 5. Friends, observe that the function f3 of t is true at t is equal to 10 seconds and later. It means f3 of t is equal to e to the power of 4t is a delayed function which occurs at t is equal to 10 seconds, meaning it is 0 for t less than 10 seconds. That you should observe. So, f3 of t can be represented as f3 of t is equal to e to the power of 4 into bracket t minus 10 into u of t minus 10. Now, if we substitute t is equal to 10 seconds, we get f3 of t is equal to 1, and as t increases, it follows the path of e to the power of 4t beyond t is equal to 10 seconds, which is shown in figure 2. So, using basic step functions, if we represent the function, we get f of t is equal to 2u of t minus 2u of t minus 5 plus e to the power of 4 into bracket t minus 10 into u of t minus 10. By taking the Laplace transforms, we get L of f of t is equal to L of 2u of t minus L of 2u into bracket t minus 5 plus L of e to the power of 4 into bracket t minus 10 into u of t minus 10. We know that L of 2u of t is 2 divided by s, and L of 2u of t minus 5 is equal to 2 e to the power of minus 5s by s, and L of e to the power of 4 into bracket t minus 10 can be written as integration between the limits 10 to infinity e to the power of minus st into e to the power of 4t dt, and that is equal to e to the power of minus st plus 4t divided by minus s plus 4 between the limits 10 to infinity. By substituting the limits, we get f of s is equal to 2 divided by s minus 2 into e to the power of minus 5s by s plus e to the power of minus 10s into e to the power of 40 into 1 divided by s minus 4. Hope you have understood it. Friends, finally consider another piecewise defined function. Observe the function. Let f1 of t is equal to 0 for t less than 0, meaning the function is 0 for t less than 0 as shown in figure. Let f2 of t is equal to 5t for t between 0 to 2 seconds, meaning the function is a ramp of slope equal to 5 units and will occur at t is equal to 0 as shown in figure 1. Next, let f3 of t is equal to minus 5t plus 20 for t between 2 to 4 seconds, meaning the function is a ramp of slope equal to minus 5 units which occurs at t is equal to 2 seconds, that you know. Finally, let f4 of t is equal to 0 for t greater than 4 seconds, meaning the function is 0 for t equal to 4 seconds and beyond as shown in figure 1. Now, limiting all the three functions for the given subintervals, we get the function shown in figure 2. If you keenly observe the function, it is true only between t is equal to 0 to t is equal to 4 seconds. Also, the function has definite values at each subinterval, that is, f of t is equal to 0 for t is equal to 0. When t is equal to 2 seconds, f of t is equal to 5 into t, which will give us 5 into 2, which is 10. When t is equal to 2 seconds, if we consider f3 of t, we get f of t is equal to minus 5t plus 20, which will give us again 10 units. Similarly, when t is equal to 4 seconds, if we consider f3 of t, we get f of t is equal to minus 5t plus 20, which will give us 0. Similarly, if we consider f4 of t, of course, we have f of t is equal to 0. Now, by representing the function f of t using ramp and step functions, we get f of t is equal to 5r of t minus 10r of t minus 2 plus 5r of t minus 4. Note, at t is equal to 2 seconds, we have to add a negative ramp of double the slope, that is minus 10r of t minus 2 to follow the given function. Further, note, we have to add a positive ramp of 5 units at t is equal to 4 seconds, that is 5r of t minus 4 to bring the function to become 0 and proceed along the x-axis. Now, straight away, if we take the Laplace transforms of f of t, we get f of s is equal to 5 divided by s square minus 10 into e to the power of minus 2s by s square plus 5 into e to the power of minus 4s by s square. Hope it is clear to you. Friends, let me summarize about what we have learned during this tutorial. The piecewise defined function may have number of subintervals. The intervals could be open subintervals also. In a piecewise defined continuous function, there will not be breaks or discontinuities. During the open subinterval, the function will be continuous. During the other subintervals, the function will be finite at both the ends of subintervals. Using the piecewise definition, the function can be plotted. Later, the function can be expressed using basic functions like step and ramp functions. After expressing f of t using basic functions, its Laplace transform could be obtained. Of course, during this process, rigorous mathematical procedure is avoided that you will have to appreciate. Hope this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.